Welcome back. So, we have discussed the eigenvalue problem for the Laplacian, and we have given the existence of a sequence of eigenvalues and the corresponding eigenvectors form a basis for the L2 of omega. With appropriate normalization, it also forms a orthonormal basis for H1 naught of omega, and interestingly you have seen that both orthonormal basis gives the same Fourier expansion. The Fourier expansion is same whether you use the normalized one or not. So, both for L2 and H1 naught the orthonormal it's a Fourier expansion is the same, and at the end we also characterized the eigenvalue, the first eigenvalue. Now, I am going to quickly recall the eigenvalues of that one. Okay. So, we characterize lambda m. Okay. So, the idea is that once you get one eigenvector for the corresponding to lambda m, you just look at its complement, orthogonal complement of that one. That is the whole idea, and then try to minimize there, and that is what will happen. So, suppose that is what we will do. Suppose V is orthogonal to, suppose you have developed everything lambda up to m minus 1. So, you look at the V orthogonal to the W1 etc. up to W m minus 1, okay, and say m greater than or equal to 2. Do that. So, once you have m equal to 2, you take W1 orthogonal to that one. So, in that case your V is equal to sigma alpha k W. So, you see you do not have to worry it is in L2 or H1, it is a same expansion for both, that is the advantage now. M equal to m to infinity, because you are looking at the orthogonal complement of this one. So, you will have to only worry about the only that one you have to see if the remaining things will not come, where alpha k as usual is equal to integral of V W k, that is enough to take, you do not have to. So, so the same analysis, I do not want to do it, if you want you can work it out, same analysis will lead to what we call it lambda m. So, exactly the minimum of RV where V is not equal to 0 and V is orthogonal to this W1 etc. W. You do not have to do anything. So, you take on the orthogonality and you have your characterization of lambda m like that. Okay. So, let me take go to the next page. So, you can also get lambda m can also be characterized as in two ways, can also be characterized by as, so let me do it one, by lambda m is equal to by maximizing this one. So, the other one is a minimizing, so just look at it, the minimization, let me show you once again. So, you see this is a minimization, all that. So, you can maximize about the vectors, all the vectors maximum of RV, then you are looking at it, V is in the span of W1 etc. and at Wm it achieves. So, the other characterization is that, so you are taking a very specific m dimensional subspace and maximizing it. So, what you can do that, you can take any subspace and maximize any subspace of dimension m and then maximize, and then it is achieved at the this specific subspace of W1 etc. W1 etc. and then you minimize over all possible W in H1 naught with the dimension of W equal to 1. Okay. So, you can have the all these both characterizations. You would have seen it if you have studied spectral theory. And to see this one is not very difficult, easy to see. So, just you work it out something, easy to see. RV less than or equal to lambda m for all V in, let me call this is equal to WM. Okay, the span of that for all V in WM, and since it is achieved, since RV equal to lambda m at V equal to WM, okay, we get the gives you the equality. Okay. And the same thing you can do it here, and so let me not do that one. The same, so when you have an arbitrary W and then you can prove that lambda m is less than or equal to that maximum, and then it is achieved at that. So, you get all this minimization, all that. So, continue this and look at the books exercise. I will leave it that. One last thing I wanted to, very important, one last property which I want to do it, and then I finish this eigenvalue problem, and little bit special property of special. I did not want to spend time on that. So, this is more crucial, special property of the first eigenpair, the first eigenpair. Okay. So, I will also leave, I will start with a theorem, and then in that I will leave some one exercise which you should work out, trivial, easy. So, it is not difficult. Let V is in H1 naught of omega. No, what is my theorem? So, let me theorem write it. Let only, but here let me not. Let W, a non-zero vector, is in eigenvector, is in H1 naught of omega, satisfies RW is equal to lambda 1, then this is something like a converse, is an eigenfunction corresponding to lambda 1. So, you already seen if W1 is an eigenfunction to lambda 1. You already seen if W is an eigenfunction, then Rw equal to lambda 1. What I am saying is that any vector Rw, so equal to lambda 1, then is an eigenvector. The proof is easy. So, you start with any V in H1 naught and let T positive, let T positive. Okay. Then W plus TV, W is the given one for which Rw is equal to lambda 1, W plus TV is in H1 naught, that is not a problem. Okay. And that hence you know that Rw, because lambda 1 is minimizer, recall that. So, Rw plus TV is greater than or equal to lambda 1, because lambda 1 is a minimizer of Rv for all V in particular. So, what is your small exercise which I will leave it? Exercise, expand the above inequality expand the above inequality. And let t tends to 0, do it appropriately, t tends to 0 will imply this one. It is a direct way of doing it. Grade W, grade V equal to lambda 1. This is what you want to prove it, to prove show that. That implies W is an eigenvector, is an eigenfunction. Okay. Okay. So another result theorem. This is very important. This is not true, very important, not true for higher order eigenvalues. It's also need not be true for other operators, even other second order operators. The first eigenvalue lambda 1 is simple in the sense that it has only one independent eigenvector. Can have any eigenvector, the multiple of that is an eigenvector, but it is not an does not have. And W1 does not change sign, does not change sign. Thus, because it does not change sign, thus we can choose W1 such that, this is important, it does not vanish also by maximum principle. So, we will see W1 greater than 0 in omega or W1 less than 0 in omega, you can check. Of course, you assume omega is connected, assume omega connected. So, try to give me, let me give a proof of this again. Proof, this is the last proof of this elliptic equation theory. Let W be be any eigenfunction for lambda 1. Okay. So, W is equal is in H1 naught of omega, keep that in mind. That we have seen this property, then its positive and negative parts WP, W minus is in. So, these are all we are using H1 naught of omega. Okay. So, this property we will see. So, therefore, you can take V equal to W plus as a test function into that weak formulation. 2 is the weak formulation, and that will give you integral of you can take W minus also. So, W plus is equal to lambda 1 integral of W plus. So, essentially W plus and W minus have disjoint supports. So, this will imply integral over omega grade W plus is equal to lambda 1 W plus. Similarly, gradient of W minus is equal to lambda 1 W minus. Okay. So, you have that. If W does not have a constant sign. You want to prove that. First I am proving that does not have a constant sign. What does that imply? That imply W plus not identically 0, both W minus not identically 0. Of course, they have disjoint support, but both of them should be. So, that will immediately implies your RW plus equal to lambda 1, that is also equal to RW minus, means you already get from this inequality, and that implies by our previous theorem. What is the previous theorem? Tells you whenever some function is in, whenever there is a function which is it's in H1 node, it achieves lambda 1, that is an eigenfunction, which is a contradiction basically. That implies both W plus and W minus are eigenfunctions for lambda 1. Functions for lambda 1. Okay. So, that means minus plus is equal to lambda 1 W plus minus Laplacian of W minus is equal to lambda 1 W minus. Okay. So, now you apply your maximum principle, strong maximum principle, and because this is greater than or equal to 0, W plus, this is greater than or equal to 0, this is greater than or equal to 0, implies W plus is greater than, and both W minus greater than 0, both are greater than 0 in omega, and that is not possible, which is the contradiction. Okay, that is a contradiction. So, the first one part is proved that W has that implies W has a constant sign has a constant sign and choose, once you have a choose entities by maximum principle you can choose W1 such that W1 is positive. You can choose W1 is negative as well. Now, to the prove that it is to prove trivial now, lambda 1 is simple, let W tilde be two eigenfunctions, of course independent, okay, to orthogonal, to we write it orthogonal or even orthonormal, you can take it, orthogonal eigenfunctions for lambda 1 such that, so therefore you get it orthogonal, right? That is you get integral of W1 W1 tilde why W1 yeah, oh I do not need that, W1 is not needed. Why did I write that? W tilde is equal to 0, but this is not possible. So, W tilde you can choose that to be positive, this to be positive, and but this is not possible, but this is not possible. Okay. So, as a final remark, the result presented above, the result presented so far, presented, it holds for that general operator, not everything, elliptic operator du by dxi, du by dxi plus a naught uv equal to lambda uv. Of course, a naught is greater than or equal to 0, smooth, all these assumptions will have that. Okay. And you have the similar variation formulation, you have the Rayleigh quotient thing, everything. So, more or less I have done this part of the course, but in the next maybe not very quickly in 5 minutes. I cannot spend much time as we are not expecting to do this. Probably this 5 minutes or 10 minutes are for numerical analysts. What is called Galerkin approximate. Galerkin. What I am going to tell is that general principle of Galerkin. General principle. Galerkin. General principle. Galerkin method. Galerkin method is not only used to approximate thing, Galerkin method can be used to prove existence as well. Okay. That is also people do use it not only for elliptic problems, even for other problems you use it. So, what is the idea? So, you have a problem AUV is equal to FV for all V in V, and then you are looking for a U in U V, looking for a U. So, the basic idea is that so you choose an orthonormal basis En, orthonormal basis for V, and then you consider this finite dimensional thing Vm equal to span of E1 etc. E1 etc. Em, and then formulate this problem one in this finite dimensional space AUM V equal to FV for all V in Vm, and you look for UM in Vm. The one of the important thing you will say that in finite dimensional spaces all norms are equivalent or spaces all norms are equivalent and you can work with basically L2 norm, that is the whole thing. Okay. So, what are the first step? Okay, 2 we already done, prove, that is trivial, that is what I am saying. Once you have an ellipticity, prove the existence, these are the steps you prove, existence of UM, boundedness, then you take weakly convergent subsequences, weakly convergent subsequence, and show that along the same, let us denote the convergence to U, show that U is a solution. So, that is not the main idea, solution, and Prove uniqueness for the main problem. Prove uniqueness, that you may have to do it. Uniqueness for 1. So, even if you are the thing, and that implies the whole sequence converges. If you get all that, whole sequence converges once you do this one. So, what's the general, how do you do this one for the getting the sequence here? So, it's a finite dimensional problem. So, you can represent because it is a finite dimensional, you can identify Vm basically with your Rm. In other words, you write your as Amj Ej, j equal to 1 to m. And for arbitrary V in Vm can also be represented as V is equal to sigma Bj Ej, and these AMJs are in real numbers. So, it is a vector for each m, it is a vector in Rm. So, a similar thing B1 here. So, you will have B is in this space here. Okay. This is equivalent to same as you are looking for your B arbitrarily, right, B1 etc. B. So, what are your unknowns? Unknowns are nothing but Amj, okay, Am1 etc. Am1, that is what your unknown. Okay. And then you can write your f also, you can write your equation eventually, you can write your 2, the equation eventually can be written as A um. I represent um in this form also. Okay. So, you can I do not change the notation. So, you represent also for this one, the same. If you do not like, you can use some other So, basically you get your A equal to some f bar. F bar is the vector coming from Fej. Okay. So, f bar f also can be written as summation Fej. This is what you do it for everything, and this is call it F1, and then you have your f bar is equal to, maybe you have to write in the column form. Okay. That is all you have to do it, and maybe you write also in the column form. Okay. Also you write it basically the corresponding component which you are doing Am1 etc. Am1. So, that. So, you will have your equation of this finite dimensional equation. A is equal to the matrix A of Ei Ej, you see, m by m matrix, and by ellipticity of small a, prove positive definiteness of A. You can see that positive definiteness of A. Okay. So, that way you derive and then you follow the procedure, and probably we will give an example through our class test. Okay. And there is another one which probably I will do it, what is about the error analysis. That is the one thing. So, there is what is called it, you are basically you try to do what you call an interpolation error. The first step in is all these things, interpolation error. That means basically error between the spaces, error between V and Vh, Vm. Okay. So, using the error analysis you will be interpolation error, and one of the theorem which you have studied in our sublevel spaces etc., we have discussed something about the interpolation error that comes in handy to do this one. But the major step, major problem, of course this error analysis is indeed a problem, but major problem is the choice of your basis. Choice of basis. How do you choose the basis? So there are interesting methods developed for the last several decades called many methods. Among them the earliest and interesting methods are finite difference method. This is more suitably is not finite difference. Finite difference is probably developed even much before, but then the one of the very prominent method is the finite element method. You discretize the domain. Using the discretizing the domain, you try to construct finite dimensional basis which is of elements for h1 naught of omega, and then you construct your VM. So there will be a decomposition, discretization of your domain. You discretize the domain and then you produce interesting finite dimensional spaces, and that is a deep big industry itself, and then deriving it. There is much more, and non-conforming methods where you don't, the spaces, finite dimensional spaces will not retain the H1 space, discontinuous methods etc. So I will more or less stop here these elliptic equations. Now from here we will move on to study the evolution equations. So what I think that you should go through the material which is the bare minimum. So we have done very little a bare minimum method. So whatever direction you want to take in the study of PDE, whether it is an elliptic equation, equilibrium system, nonlinear equation, specific equations like conservation laws, or fluid flow equations, any equations where you want to study in the modern setup, you should go through what you have done. So this is only the beginning of the tip of the iceberg. Okay, the ice, you have to do it. So I will stop here with this all elliptic equation. We will study more about evolution equations in the coming next 20 lectures. Thank you. Thank you.